Today, you are going to learn about the second super ridiculously important mathematical tool slash fundamental operation in all of calculus. Do you guys remember what the first one was? Anyone? Anyone? It was differentiation. Differentiation was the first one. So the second one, can you guess? The second one is actually, I don't know if you guys could hear that, but that was a record scratch that I normally can have in class, but you know, I tried. Oh well. No, actually, so it is adding, but we're actually going to be adding, there you go, in case you didn't hear it the first time, an infinite number of times. So many, in fact, it's considered indefinite. Indefinite, what the heck does that mean? I don't even know. Let's keep going. Okay, so yesterday, we found or previously, not necessarily yesterday, but previously, we had the area of, the actual area under the curve. So we started out with an approximation. Then we took the limit of that approximation as n goes to infinity, and that became the actual area under the curve, okay? So one thing that I left out on purpose the other day, because I didn't want to scare you guys, because I think you can handle it now, is that this is actually what is called a Riemann sum. The guy named Reimann is the one who coined this phrase here as having the actual area. Like basically anything that has a delta x here is considered a Riemann sum. He is the one that basically discovered this process, okay? So since we use it to find the area under the curve, we could now also say that the exact area, with the limit definition, my new notation is to call this the integral. There it is. I know you guys have been waiting for integrals for a while now. Finally found them. The integral from a to b of f of x dx. Now, another way of looking, like this is what we did yesterday or previously. Another way to look at this is to, what some people prefer to do is instead of using an infinite number of rectangles, they instead create an infinite number of rectangles by making delta x infinitely small. I mean, it works out the same either way. So that's why sometimes in your textbook you might see this, and also depending on your professor, when you go to calculus next year, they might do it this way. The overall process would work exactly the same in the long run, because they both turn into the indefinite, or in this case definite integral, from a to b of f of x dx. All right, well that's great, very well and good. How do we solve these? Okay, so let's say you have, I want to evaluate the definite integral as a limit. Okay, what on earth does this mean? So graphically, this is what is happening here. Okay, so I am taking the integral of my function. My function is 2x. This is a linear function. Oh, let me write this in a different color. This is a linear function with the slope of 2. And I'm going from -1 to +2. So -1, +2. So I want to find the area between the curve and the x-axis. So let's see. So this and this right here. Okay. I want to find the area of these two things for the function 2x. Okay. So the first thing we're going to do is we're going to rewrite it as a limit like we did the past couple days. So we've had, typically they give it to you as f of x is equal to 2x, and then we're evaluating it from -1 to 2. And before we were given a set number of boxes, but now we don't have a set number of rectangles or boxes. Instead we just say, I need to find the area under the curve using the limit definition. So remember, area is the limit. Oops, that should be a K. Okay, so knowing this situation, I've got delta x is equal to 2 minus -1 over n, so 3 over n, and c sub k is going to be -1 plus k times 3 over n, so -1 plus 3k over n is c sub k. So I'm going to plug that into my function. So the limit as n approaches infinity k equals 1 to n. My function was 2x, so 2 times c sub k, which is this guy right here, so negative 1 plus 3k over n, times my delta x, which was 3 over n. Okay, so from here I'm just going to try to clean this up a little bit and say the limit, whoa, come on now, the limit as n approaches infinity, k equals 1 to n. So I've got negative 2 plus 6k over n times 3 over n, which becomes n approaches infinity of, I don't need parentheses anymore, negative 6 over n plus 18k over n squared. So far so good. Everybody's still okay? So I've got the limit as n approaches infinity of negative 6 over n, k equals 1 to n of just 1 plus 18 over n squared, k equals 1 to n of k. Infinity of negative 6 over n times n plus 18 over n squared times n plus 1 over 2. Okay, and then from here I take the limit, n approaches infinity, this is negative 6, this is going to become 9n n plus 1, the 2 and the n, or the 2 and the 18 reduce for n squared. This is just negative 6. This is a balanced situation. So then my limit is just 9. So then overall, the area is 3. Now, some of you are going, why on earth did we do that entire long process when we could just look here and I have two different triangles. Triangle here, triangle here. I can find the area to add them together. I completely agree with you. I see what you're saying. Okay. But the reason I showed you with a simple problem is because eventually we will do more complicated ones. And I wanted you to understand what's happening on the simple side before we get to the more complicated process. Okay. So if I wanted to evaluate a definite integral as a limit, there you go. You guys are rock stars at this now. Okay, so that's how you would do it. And this is a very typical question for us to ask. It's like, hey, here's the integral, but evaluate it as a limit. Okay. To do that, you have to use the limit definition of area, which is this guy right here. Okay, let's see what else we got here. Now, rewrite the integral as a limit, but do not evaluate. Oh, so this is nice. So they don't want you to actually go through the whole process, but they at least want you to set it up as a limit. Okay, again, we already know this process now, so let's see what we have here. So this right here is my lower bound, this is my upper bound, so 1 to 6 is my a to b, and then my function itself is x squared. Okay, so we're going to start with finding delta x, which is 6 minus 1 over n, so 5 over n, and then I need to find c sub k, which is going to be a, so 1 plus k delta x, so 5 over n, so 1 plus 5, 1 plus 5k over n. All right, so then the limit as n approaches infinity of the summation from k equals 1 to n of my function, which is just x squared. So I want c sub k squared, so 1 plus 5k over n squared times delta x, 5 over n. Okay, so I don't have to evaluate it. Okay, so I took this right here and I turned it into that. Now, it's also very common for us to ask you to go in the opposite direction. Okay, you're going to have an activity either later today or possibly next class, depending on the time, where you practice going back and forth between the two of them. Because it's a very common thing for us to ask you to do, and you'll see this a lot again in years to come. Okay, so actually, speaking of, I have a link posted in Canvas. Normally, I would just go to this link directly in class and we would do it all together, but you're going to just do this on your own. There's a link posted in Canvas called Khan Academy Definite Integrals as a Limit of a Riemann Sum. Go to that. It's going to give you 3 or 4 practice problems. I think it's just 3, but you're going to pause here, do that, and then come back to this. If you wanted to, I guess you could do it later, but my intention is for you to do that right now. So go ahead and do that and then come back. Okay, so assuming you did that, what other methods could we use to find a definite integral without necessarily using limits? Let's think about these functions here, okay? So I have the function from 1 to 3 of 4. My function is simply the constant function 4. So if I were to think about what this looks like graphically from 1 to 3 up to 4, well, that's the constant function. So the f of x equals 4 is just the constant function. But I only want it from 1 to 3. So it's essentially just this little bit of area. Whoa, too much. I had a feeling that might happen. I don't think I closed that all the way. Let's try this again. I want just that little guy right there. Well, that's... Hey guys, we have a square here. Not a square. My bad. It looks square. That's because I didn't draw this to scale. So the height is 4. The width is 2. Hey, the area is 2 times 4, which is simply 8. All we had to do here was just use our geometry skills. So all of these we can evaluate using geometry. And we don't even have to use limits at all. Oh, that's so nice, because sometimes those take a while. Okay, let's think about what x plus 2 looks like. Well, that's the linear equation. Slope of 1, y-intercept of 2. So 1, 2. I'm going from 0 to 3. So boom, boom, looks like that. But I only want from here to here. Let's see if I can shade it in correctly this time. Oh, perfect. Okay, well, hey. What shape does that look like to you guys? Looks pretty familiar. Kind of like a trapezoid. Oh, no, I meant to 3. So the distance here is 3. The height here is, well, actually, I should say the height of my trapezoid is 2. Base 1, I'm sorry, the height of my trapezoid is 3. Base 1 is 2. I needed to figure out what base 2 is. So, I just plugged 3. Okay, so that's going to be 5. So the area is going to be 1/2 base 1 plus base 2 times your height. So I get 7, right? 5 plus 2 is 7. Yeah, nope. Wait a minute. I did it again. I am so sorry, guys. That is not supposed to be a 2. That is supposed to be a 3. 3. The height is 3. Murphin will get it right at some point. You know what? We're just, yeah, it's fine. 5 plus 2 is 7 times 3 is 21 over 2, which does not reduce with a 3. So 21 over 2. That makes much more sense. Okay. What about that last one? From negative 2 to 2 of the square root of 4 minus x squared? What parent function is that? Do we have that memorized? Yes, I believe Murphy told us to memorize that at one point in our lives, but I don't remember what it is. It is the semicircle function. Boom. Boom. And I bet it goes from negative 2 to 2. You are correct, it does. So I need to find the area from here. I want both of those things. So instead of using the area under the curve, using the limit definition, because I think that takes me way too long. Hey, it's a semicircle with a radius of 2. So the area of a circle is pi r squared, so I want half of that. So pi times 2 squared over 2, so it's just 2 pi. Okay? So, ta-da! That is how you can find the area under the curve using just geometry, not even the limit definition. How convenient is that? Okay. All right. So, some boring but really important details you need to remember about integrals. Okay. So, first thing is continuity implies integrability. If a function is continuous on the closed interval from a to b, then f is integrable from a to b. So what that means is if you have a function that looks like, I don't know, this right here. Hey, that looks familiar, I think. That tends to be one I draw a lot. I can take the integral of that because I can find the integral underneath all that stuff. It works out nicely. If I have a function that looks like boop, doot, doot, okay? It's a piecewise. This is legit, okay? Overall, this thing is not integrable, okay? I could integrate each individual piece and then combine those together, but as a whole, a function is not considered integrable unless it is continuous. Okay, remember how with differentiability, in order for a function to be differentiable, it had to be at least continuous? Same idea here. For a function to be integrable, it must be continuous. Okay. All right, and then let's see what else we got here. Special definitions. So if f is defined at x equals a, then we define the integral from a to a of f of x is equal to 0. What? What would that even look like? Let's say I have my usual curve that I like to draw on a daily basis. Okay? I'm evaluating it from a to a. So basically I want the area of this thing right here. Well, a to a, that's not going anywhere. You're staying in the same spot. So essentially, you have the area of this line right here. Well, a line is it has no area. Like it's a one-dimensional concept that goes on and on forever in two directions, but it has no width to it. So because you are just looking at this line right here, there's actually 0 area. So the integral from a to a of any function is just 0. Last one here on this page. If f is integrable on a to b, then we define the integral from b to a of f of x dx is equal to the negative of a to b of f of x dx. What on earth? Here's how this works. So remember when we did the limit definition of an integral, and one of the first things we would have to do is to find delta x. We would say b minus a over n. Okay, well, in this case, now a and b are in opposite locations, and that's fine. You can do that. But when they're in the opposite locations, that means they're going to have the opposite effect. Like when you say b minus a, it would have the exact opposite effect. So, for example, if I had my integral set up from 2 to 4, blah, 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 you know, dx, then my delta x would be 4 minus 2 over n. Okay, well, if I set up my integral instead, 4 to 2, blah, 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 dx, my delta x would be 2 minus 4 over n. Here, this is 2 over n. Now it is negative 2 over n. Okay, so you are allowed to do it this way, but basically it's saying like, hey, if it's ever written in this format, go ahead and flip it back over to where these two numbers are in numerical order, because that's what we're more accustomed to, but pop a negative out front, because that's going to be the effect that it has. Okay? All right. Moving along. Oh, we have more properties. Ah, yes. Let's see. Ooh, the additive interval property. If f is integrable on the 3 closed intervals determined by a, b, and c, then we have, okay, the integral from a to b of f of x is equal to the integral from a to c of f of x plus c to b of f of x. What? Okay. Here's my function. Here's a. Here's b. Here's c. Okay? The area of all of this, okay, is equal to the area of this plus the area of that. That's essentially what they're saying, which makes perfect sense. We had angle addition properties back in geometry. This is kind of like the integral addition property, okay? Makes sense. I don't know why it's called interval. I feel like it should say integral, but you know what? I didn't write the book. I'm not in charge. I just go with what they say. Okay, let's see some other properties. Let's see here. All right. So if f and g are integrable on a to b and k is a constant, then the functions of k, f, and f plus or minus g are integrable on a and b, and you have these two properties. What? This is just a scalar multiple. Okay. We did this when we did summations not too long ago. So just like you can have a scalar multiple inside the integral, you can also just pull that out front, solve the integral, and then multiply it at the end. You know what? Sometimes you want to do one, sometimes you want to do the other. Do you. Whatever's fine. Okay? Just like you can add sums together, because remember, the whole point, all of these things, all of these integrals come back to a summation, and then we take the limit of that summation. So if you can add and subtract summations together, you can add and subtract integrals together as well. Okay? Same overall concept. All right? Let's see what else we got here. So if f is integrable and non-negative, ooh, that's a big word. Non-negative. That means it could be either 0 or positive. Non-negative does not mean positive. I'm going to repeat this one more time. Non-negative does not mean positive. Non-negative means that something could be equal to 0 or it could be positive. Okay? So if f is integrable and non-negative on the closed interval from a to b, then 0 is less than or equal to the integral from a to b of f of x dx. Well, that makes sense. I mean, the whole function is non-negative. So that means the area would be, so like if my function looks like, so it's non-negative, so it could be equal to 0 or positive. Okay, that means the area under the curve, all of this stuff right here, would also be greater than or equal to 0. Oh, that makes sense. Okay. If f and g are integrable on the closed interval, and f of x is less than or equal to g of x for every x in a, b, then their integrals are less than or equal to each other. Well, that makes sense. Let's say f of x looks like this. Here's f of x. And so then the area of f of x would be all of that stuff right here. Let's say g of x was greater than or equal to, so there's g of x. Well, that means the area of g of x would also be slightly, well, it would be greater than or equal to the area of f of x. That just seems pretty straightforward, okay? So now you are going to apply these things to a properties of integrals worksheet next. So you're going to get this worksheet from the sub. They're going to give this to you. You're going to work all the way through it. I have a video sort of kind of from years back of me going over that worksheet. I'm going to attempt to edit that and put that in here. No promises. It might be a separate video in and of itself. But either way, that's the end of our video for the day. So you're going to finish up this worksheet and then move on from there. As always, when you have questions, Khan Academy, Prof. Rob Bob, and your textbook.
Okay guys, welcome back to Properties of Integrals, or actually Definite Integrals Part 2. You should have already finished up your Properties of Integrals worksheet. So I'm going to real quickly go through the answers here, and if you have any questions, ask a neighbor for some clarification, or you can always ask me in tutorials later on today or tomorrow. Okay, so number 1, for Part A, our answers are 4, 7/3, and -1/3. Down here we've got 23, 13, and I'm pretty sure this was nowhere to be found in our notes, therefore it does not exist. It's not a property. So this is no such property. There is no multiplication or product rule for integrals. Doesn't exist, not a thing. -6, 16, again we've got something that looks a little strange. This looks like a quotient. There is no such property. Not a thing, doesn't exist. This last one, you can add them all together and you get 12. Decide whether this statement is true or false. This statement is true. If for any choice of real numbers a and b, and then f of x equals 0 for all x and r. This is true because if no matter what, if I pick random numbers the whole time and I always get 0 for my integral, the only way for that to happen is that a and b are 0 every single time. So this statement is true. Number 4, let f be a continuous function on the interval from -5 to 10. G of x equals f of x plus 2. If this is true, then what is g of u du? It doesn't really matter what variable you use. I'm sure you guys are probably like, what? There's x's, there's an x here and here, but now we got t's and then u's. Doesn't really matter. The property is all the same. We're going to work this as from -5 to 10, f of u plus 2 du is equal to the integral from -5 to 10 of f of u du plus the integral from -5 to 10 of 2 du. So you're going to get 4 plus 30, which is 34. Okay, so that's your properties of integrals worksheet. Again, this is going to go inside your notes with everything else. So if you want to, you can tape it in.